Hello everyone. Today I'm going to start chapter 15. It is about multiple integral, and in this video clip today I'm going to cover the first three sections of chapter 15, section 15.1 all the way to 15.3. It is about double integrals. Okay, but first let's recall something that you guys learned in Calc 1. I think it's the end of Calc 1 about the definite integral, definition of it. Because what you have single variable function. Say you got a function f, which is above the x-axis, okay, and this is the y-axis, and our definition of definite integral from a to b, fx dx. So from a to b, this is a, this is b, this is the area of the region bounded above by the function f, below by the x-axis, and the two vertical lines of x equal to a and x equal to b. And the idea that we learned in Calc 1 how to calculate this area is what? We chop it up into many columns, and then we calculate the area of each column at a time. So dx is like a very tiny bit of the width right here. This is like dx, and dy, I'm sorry, f of x, dx is the width, and then f of x is like the height. Okay, so you take the height times the width. You have the area of a very single little tiny column that you add all the area together. You have the entire area for the whole region, and this is how we define, pretty much, how we define the definite integral of f of x dx from a to b integral. Okay. Now we're gonna carry the same idea into Calc 3. Instead of single integral, now we got double integral. So let me draw it in 3D. Okay. Say I have this. This is my x-axis. This is my y-axis. Let me draw it a little bit smaller so I have some room to write. Okay. X-axis, y-axis, and it's my z-axis right here. And then this is my function fxy. This is fxy, which is the surface, and assume that it's above the xy plane, okay? And you want to calculate the volume. Now it's not area anymore, volume. Volume covered by, upper by the function, and then xy plane and the region. Say x run from, let me make it a little bit more general. From, say, a to b for x, and then y run from c to d. Okay, so this is what I'm talking about. All right. Well, this is the volume of that big column that you have right here. Okay, and the base is the region. Instead of a from a to b for one-dimensional space, we have area a to b for x, and then c to d for y. And you see the column right here, covered upper by the function, lower by the xy plane, and then the rectangular shape. That's the idea. And we know this way in double integral, okay, of the region. Let me just call it r. R stands for region. In here it's rectangular, okay. Of f of x, y, dA. A here stands for the area. So the idea is this: we're gonna chop it up into many little columns. Okay, a little bit. Let me use a different color. A little bit. Okay, and then we word up. All right. We're gonna like this. Okay, and we calculate the volume of the little tiny column. This one is dx, and then this one's dy. So we calculate the little area of the base, which is dx, dy right here, is dA. Okay, this is double integral f x y. In this particular case, it's dx times dy, where dx is a little change for the x-axis, and dy is a little change for the y-axis. Multiply together, you got a little change for the area, and multiplied by the height, you have the little volume. And then Now x is inside, so we start with integral x first, run from a to b, and then y outside, run from c to d. And this is how we define the double integral. So you think of it like the volume, okay? Volume bounded by the function and the 4 vertical planes going up, and then the rectangular on the bottom. And you can write this way if you like to. Double integral, right? F xy dy dx. Now dy is inside here, you have to write what? C to d for y, and then a to b for x. Okay. Pretty much that's our definition. And let me show you how to actually calculate this integral, definite integral, double integral. Okay. With the boundary. So example, let me write it here. Integral, double integral. How about this? X y squared plus x squared y. Let's make it easy. Dx dy. X run from 0 to 1 and y run from 0 to 2. Okay. So it's not really hard. It's just more work to do because you have to do integral twice. So first of all, we do inside out right away. Take a look at this from here to here. We're gonna take care of this integral in terms of x. So think of y as like constant, like when you do partial derivative. So think of y as a constant. Integral of x y squared is 1/2 x squared y, right? Okay. And integral of x cubed y, x squared y in terms of x is what? 1/3. All right, 1/3, right? X cubed y. You see? Take the derivative of x, you got what? 1/2 x squared is just x y, and then 1/3 x cubed y. Derivative is x squared y. And this one run from 0 to 1. Okay. So you plug in, you know what means by the boundary. Plug in x equal to 1. You have something, subtract x equals 0. I chose easy numbers, so we don't have to do a lot of math. The different numbers, say 2 to 1 or something, then you have to do more work. But same idea. Plug in x equal to 1, I got what? 1/2 y plus 1/3 y, right? And then, of course, so x equals to 0, you got all 0. And this is what? 1/2 plus 1/3 is 1/2. Common denominator is 6, so this is 3 over 6 y plus 2 over 6y. So this is 5 over 6y. So our integral becomes what? Integral from 0 to 2 of 5 over 6y dy. We took care of the interior integrals, right, in terms of x. You have this. And then what? 5 over 6y integral will be 5 over 6 times 1/2 y squared, run from 0 to 2. And of course, you can plug in numbers and you can calculate y. Okay? And sometimes it could be easier the other way around if you interchange the variables. You can do what? Integral, double integral, x y squared plus x squared y dy dx. And if you want to do it this way, dy y going to run from 0 to 2 for the interior integral. You have to take care of integral of y first, and then what? 0 to 1 for x. I claim that you guys are going to have the same answer. However, with this way of writing, then you have to do integrate into y first. So it's going to be what? 1/3 x y cubed plus what? 1/2 x squared y squared. Right? Run from 0 to 2 for y. You plug in, you have value of x, and then you integrate x from 0 to 1. Okay, same idea. So far, so good. So actually, it's not really too hard. With first examples right here with you, see what? Double integral, just work inside out. Okay, and the meaning of it geometrically is the volume bounded by the function and the 4 vertical plane and the xy axis. Okay, so far, so good. There are some special cases of double integral function. I think it's going to be helpful for you guys when you do the math. If the functions are separable, say for example, I'm going to give you another one, double integral. Okay, so x run from the x, the y, x inside run from a to b, and y from say c to d. The thing is, I try to emphasize about the function. If you have something like this, say x square y plus 2xy, for example. Okay, and if somehow you can separate the function inside, this is the function inside two variable function x, y, right? If you write this way, x squared plus 2x times y, you see what I've done? I just factor out the y, right? So you see what? All the thing in parentheses in x term, all the thing in y, and the other thing outside the parentheses y term. Another way, you can separate the two variable function. Becomes the product of two single variable functions. So somehow you can write this as what? Say f of x times g of y. And you can think of what? Do the integral, single integral twice. So this is the same as what? Integral dx, right? X is x squared plus 2x times dx, run from a to b, and then you calculate the integral of y, run from c to d, dy. See? So no more double integral. It becomes product of two single integrals. Okay? So if you're lucky enough, that would be the first thing I would check. If somehow some problems, or actually it's quite a number of problems you see in your homework, if you can separate the two variable function into the product of two single variable functions, then I would strongly encourage you guys to do the integral this way. It's going to be easier. Okay? And you have this number, and multiply our number, but you have the answer. It's the same. Okay? So you guys see some idea of double integral function? It's kind of carry over from count one that you got single variable function, right? The area of each column, then add them up, you have the area for the entire region. Now, 3D, we don't talk about area anymore, we're talking about volume, right? So we calculate what? The volume of one little tiny column, and how to calculate it? Base area times the height. Base is what? Dx, a little bit, dy, a little bit of change in y. That's dA, little area, and times the height, which is a function value. You have the little area, and then you add all them up. So we deal with two variables x and y, we do double integral. Okay. And if all the boundaries are constant, x run from a constant a to b, y run constant c to d, then you can interchange. Right? Instead of doing dx dy, you can do dy dx. Okay. And some other cases, if your function is separable, you cannot separate them, become the product of two single variable functions. Like in this case right here, then you can apply a single variable function, you multiply them, two integrals together, you have the same answer. And I claim that many times this turned out to be easier. Okay. Now let me move on to some more advanced cases of double integral. I'm moving on to section 15.2. Let me see if I'm missing anything on 15.1 first before I move on. I see that the book is talking about average value. It's not hard. It's just I forgot to mention 15.1. Sorry guys. Come back to 14. 15.1. Okay. Average value. Average value. So this is the idea. So this area, so talk about count one, we learned right here. The area is that much, right? So the function can run from, when x runs from a to b, the function may go from this point, go up and go down, right? So in average, what is the value of f when x runs from a to b? So think of this area, the whole area is that much, right? What if you take the entire area divided by the distance from a to b? Okay, then you're going to have the average height, because this is the area, and you divide by one side, you have another side. So the function average AVE stands for average. So some people just write F and then with a bar on top. Is 1 over B minus A times the integral from A to B f x dx. And graphically, show you the line right here, line right in the middle. So you what? This is F average. Okay? So the area of that region is the same thing as the area of the rectangle right here. Okay. Good. F changes up and down, but in average from when x runs from A to B, F is about that much. Okay. The area of that window shape is going to be the same thing as the area of rectangle. Length times the height, F average. Okay. See, F average times the length right here is the area of the rectangle is equal to the integral, which is the area of the region. And same thing here. This surface curve right here, surface function right here, could be up and down. Remember we learned about local max, local min will be up and down, right? And you want to calculate the average function, fxy. Right this way, or f average. Okay, two variables. Okay, it's gonna be what? Integral, double integral over the region R, f xy dA. I'm just writing using our book notation. dA is, the whole thing right here means the volume, and then you have to divide the volume by the base area. Okay, the area of the region R. So in this particular case, you do what? B minus C times B minus A, because B minus A is the change in X, and B minus C is the change in Y. So length times the width, you have the area of the base. Okay, I'll write it in general. It's gonna be the average function. That's all. And that is the end of 15.1. Let me move on to 15.2. I'll be talking about some more special area region. The base may not be nice as a rectangle like this. Okay. And how we're gonna take care of it. Yeah. Because we emphasize in the domain, the region, so let me draw it this way. This is my x-axis, this is my y-axis, and I want you guys to imagine that the z-axis is coming out of the board. Okay, this is our z-axis coming out. Okay, origin right here, z coming out. And if you have the regions R, looks like this. So x run from A to B, which are constant. However, y's are not constant anymore. Y is a function in terms of x, so y run from f of x to g of x. Okay, so you're seeing that y is not running from C to D anymore. All right, y is changing. The lower bound is a function f, and then the upper bound the function g. In this case, you cannot interchange the variable of x and y anymore. Double integral over this is my region R again, of the region R of f x y and dA. By the way, fxy is the function right here. The y-axis coming out, so the function fxy is the surface up here, okay? Right above that region. You cannot interchange the variables anymore. You have to write the one with constant outside. So the x is going to be outside because x is going from A to B. And then dy is going to be inside. Now y run from where to where? From f of x to g of x. Okay? And the function fxy inside. And then you calculate the integral. Give you an example. If I have the integral, say double integral, dy inside dx outside, x run from 0 to 1, choose easy number. Okay? Say y run from say x to x squared, for example, and make a simple function, 2xy. Okay. And by the way, this one is not constant. You cannot even separate the two functions. You have to do this in this order: dy first, and then dx outside. All right. So now we're gonna take care of the part, the integral that inside the other integral. 2xy dy integral is going to be xy squared, right? In terms of y, x is a constant now, and that run from x to x squared. Let me write a little bit clearer. Say what? Y run from x to x squared. If run this way, hopefully it's a little bit clearer. So you guys see which one's a variable. Okay, so y is a variable. So you plug in y equal to x squared. I got x times x squared square, subtract x times y equal to x. So x times x squared. Okay, this is what? X to the fifth minus x cubed. Alright, so the integral inside the interior integral is y is a variable, x is a constant, and y run from x to x squared. Okay. People use this just for x to x squared, but if you want to be clearer, you can write this way. Y equal to x over y equal to x squared, and then this is x equal to 0 all the way to x equal to 1. And that helps you to see clearer if you want to. Now I gotta integrate this from 0 to 1 dx. And you know how to work with this. This is 1 over 6, x to the 6 minus 1 over 4, x to the 4, run from 0 to 1, which is 1 over 6 minus 1 over 4, which is a negative number, right? Common denominator is 12, so 2 minus 3, so negative 1 over 12. See? And similarly, there's another case that you have to change. What if I have the function where y is a constant and x changing? So you have such a thing like this. So y run from c to d, x from h of y to k of y. Okay, now this y is a variable. Okay, x is the function. And guess what? You're gonna write this way: integral, double integral, right? Now y is a constant, so y gonna be outside, dy outside, and dx inside. Still f xy. Okay, and variable x run from what? H of y over k of y, closer to further, and then y run from c to d. Same idea, just interchange. If you see the shape like this, y is constant, x a variable, you have to integrate x first and y out. And the other way around, x is constant, x is outside. Anyway, constant gonna be outside, function stay inside. And of course, you can think of, I'm just talking ahead of time. You can think of integral, triple integral. Right? You got what? Dx, dy, dz, okay? But that's what we're gonna learn later on. It's just double integral for now. Okay, and this is the whole idea for 15.2. It's about double integral over some general region instead of rectangular region like we have in the definition. Okay, let me see if I missed anything on 15.2. Nope, that's it. Oh. I think this is helpful, but I guess you guys know already. Say you have a region in general. Okay? And you want to cut it off into R1 and R2 this way, then the integral on the double integral on the region R is going to be equal to double integral on the region R1 and plus double integral on the region R2. Okay? It doesn't matter how you cut it, it's going to be add them up. So the idea is what sometime if the general region is kind of hard to work with as the whole, that's the entire thing at once, then you may have to cut it up into some nicer shape. That'll be easier for you to do the integral. And I'm going to leave that part for you guys for your homework, okay? And one more thing, you may have more than one way to cut the region up, okay? So it's up to you to think. It's similar to this, single integral from A to B, right? You can cut it off, integral from A to C, and then plus integral from C to B. Remember, in Calc 1, same idea here. If the entire R is equal to R1 plus R2, then you can do the same idea. Okay. And this is officially the end of 15.2. move on to 15.3. We're still talking about double integral. Now we change the coordinates. Instead of talking about rectangular coordinate x and y, we'll be talking about something called polar coordinate. Okay? So what is it about? Say you have a region like this. Say this is x-axis, y-axis, and again, one more time, I want you guys to think of the z-axis. This is the arrows that's coming out of the board. Okay? Say if you have a region like this. Okay? So this is the region that I'm talking about. The region of it. Okay? Is where the angle run from, say, alpha 1, say alpha to beta. Then alpha. Used to people use Greek letter for angle. So this is the angle alpha, and this is the angle beta. Okay? And this is the function R1 theta, and this is the function R2 theta. Okay. Function into a polar coordinate, something you guys learned, I think, in what's that? Top 2. Okay. So you want to calculate the area bounded by the two function R1 theta and R2 theta, where the angle run from alpha to beta. Okay. This is the formula: double integral of f x y dA. Again, this definition that we have of fxy is a function up here, all right, and then dA is the area. But you want to do is in polar coordinate, you have to convert all xy into r and theta. And we talk about polar coordinate. And we have a formula to change. I think x is equal to r cosine theta. And I assume that you guys know this already. That's why I'm running fast, okay? If you don't know, then please go back, or maybe you'll have time at the end. I'll come back to this. And y equal to r sine theta, okay? And you have to calculate the little areas. Is dx dy going to be changed to dr d theta. And this is what it is. dx dy is equal to r dr d theta. So, let me explain the whole thing for you, just in case you don't remember, because we have this from top 1. Okay, so we have a point on the rectangular coordinate, x here, y here. This is x comma y. So this is x, and this is y. Okay, so you want to calculate theta, which is the angle right here. And you want to calculate r, which is the distance from the point to the origin. So what? X squared plus y squared by Pythagorean theorem is going to be r squared, or r is equal to square root of x squared plus y squared. And theta right here, you can use tangent. Tangent of theta. Tangent is opposite over adjacent, so y over x. So you got from x, y, you can change to r and theta. The other way around, if you have a point on the polar coordinate r and theta, you can calculate x and y. Okay, so this one now is what? R and theta. Okay, you got r and theta. You can calculate x, right? You got the hypotenuse of this right triangle right here. You got the angle right here. So x right here is no more than what? X is cosine, right? Adjacent over hypotenuse is cosine of theta. Okay? So cosine of theta is x over r, and of course x is equal to r cosine theta. Similarly, sine of theta is y over r, so y is equal to r sine theta. So that explains how we have the formula right here. X is r cosine theta, and y is equal to r sine theta. Okay? And then what about dx dy? So instead of thinking of dx dy is like this, right? This is dx, and this is dy.